If we're going to apply the mean value theorem, first we got to verify that this function on this interval satisfies that theorem. All we're going to do to start is we're going to say that f is continuous on the closed interval as it's defined. It's defined here as -4 to 1. And f is differentiable on the open interval, -4 to 1. Okay, we can conclude that based on this domain restriction because we know this function right here, that's a quadratic. So its graph is a parabola. We know it's going to be continuous. Right? We're not going to have any little breaks in the graph. We're not going to have any little corners in the graph, which is why it's going to be differentiable. So we can state all this, and as long as we can state all this, then we can say that this mean value theorem holds. It works. And if we apply it now, for our calculation portion here, we're going to set up two sides. On one side, what we're going to do is we're going to take these values that make up our domain here, essentially set up the endpoints of the graph that we're looking at. We're going to plug those into the function. So I'm going to take -4, I'm going to plug in. I'm going to take 1 and plug in. If I take -4 and I plug back into the original function, well, let's see, I got -4 squared 16. Basically, you're subtracting 8, right? Adding 1, so we're going to get 9 back. If I take 1, plug into the original function, now I got 1 squared plus 2 times 1 plus 1, so that's going to be 4. So take these values that make up our endpoints based on the domain here, plug them into the function, find these corresponding values of the function or y values, and now we're going to find the slope of the line that would pass through these points. So to find our slope, we take the difference in our y values, which is the difference in the values of the function here. Take 9 minus 4 over difference in the x values. So -4 and 1, those are the x values, subtract those. Get 5 on top, -5 on the bottom, slope is going to be -1. So playing with the function exclusively over here to help us find the slope of the line that goes through these points that make up our endpoints on this function. We get -1 back, and we now use that over here. Okay, we use that over here in connection to our derivative. So let's take our derivative. Derivative of this function, pretty simple, 2x plus 2. What we're going to do is take that -1, we're going to set that equal to the derivative of the function, because in doing so, we're going to be able to find these values of c based on our mean value theorem. So in finding values of c, this is what I would do. If I'm going to set this equal to the derivative, instead of setting this equal to 2x plus 2, set it equal to 2c plus 2. Take the x's out, put c in. Of course, if you don't do it that step, not the end of the world. You solve for x and you say, all right, this x represents this c value idea. But if I solve for c, subtract 2 over, divide by 2, finding all possible values of c based on this mean value theorem, we find that c is simply -3/2. So if it's just like the last one, we start the same kind of way. We start by establishing that the function is continuous. It's continuous on this closed interval as it's defined, 3 to 6. And f is differentiable on the open interval, 3 to 6. And if we can conclude that, then we can say, therefore, this mean value theorem that we're trying to apply holds. Now, the reason we can conclude this, dealing with the radical function here, well, let's think about this for a minute. Square root of x. Y equals square root of x looks like this, right? Minus 2 moves it 2 to the right. So there's that curve. We're looking at that curve from 3 to 6. So we're going basically from this point up to this point. We can see how it's continuous. We can see how there's no corners there, right? No breaks. So it has to be both continuous and differentiable. Now we know we can apply this theorem. We go to the calculating portion of the problem. Just as we did on the last one. We're going to take our values that are up here from our restrictions on the domain. We're going to take those values and plug into the function. We get the corresponding values of the function back at those values of x, or the y values at those values of x. You take 6 and plug back in the original function, you got the square root of 6 minus 2. So you get the square root of 4. Get 2. Take 3, plug in, got the square root of 3 minus 2, so that's square root of 1. Get 1. So we're going to do that to find the slope of the line that is essentially going through these 2 points here. So take your difference in your y's. You've got 2 minus 1. Over your difference in your x's, you've got 6 minus 3. Slope of the line through those endpoints is going to be 1/3. So remember, we're going to take this value here, and we're going to use it over here. Before we can use it over here, though, we have to take the derivative of the function. Taking the derivative of the function, you've got x minus 2 basically raised to the 1/2. Bring your 1/2 down. X minus 2 left. Subtract 1 away from that power 1/2, get negative 1/2. Tack on the derivative of the inside. To complete the chain rule, that derivative would be 1. Go into simplifying mode here for a moment. We know we're creating a big fraction out of this because of that negative exponent. We know this is all lumped together through multiplication, so that's all going to make up this fraction somehow. Got a denominator of 2. We take this quantity here of x minus 2, bump it down to the bottom, make that a positive power 1/2. Everything else goes on top, so everything else would be 1 here. So there's the derivative. We're going to take this piece, we're going to set that equal to our slope, and we're going to solve for however many c values we're going to get here. So as I do that, let me carry this over. I got 1 over 2 times the quantity, short-term memory here, it's c minus 2 raised to the 1/2. Since I'm solving for c, I'm going to go ahead and insert c in the place of x. That equals that slope of 1/3. Okay, one way to go about this, could cross multiply, right? Got 1 times 3. You got 2 times your quantity of c minus 2 raised to the 1/2 times 1. Okay, at this point, again, trying to solve for c, I might divide this 2 over to try to isolate that expression right now that's got the c in it. If I divide that 2 over, got 3/2 equals, I'm going to change this to square root of c minus 2 for calculating purposes, actually for solving purposes. If I change that over to a root, I can see a little bit better now how if I square both sides, I lose that root. 3/2 squared would be 9/4. Losing my root over here, I got c minus 2. Meaning, if I add this 2 over, finding a common denominator of 4, that'd be 8/4, right? C is going to come out to be 8 plus 9, 17 over 4.